If you take calculus, one of the most important concepts that you will be introduced to is the derivative. It's one of those things that we spend several months going over, so don't expect to understand it completely after today. You're just going to get just like a 10-minute or 20-minute video, so you probably won't have a huge understanding of it, but I'm hoping that you get a little understanding of it. So I want you to recall a few things from geometry. If you notice, I have a circle with a line that touches the circle at two places and actually goes through the circle. And then I have another line that touches the circle at only one place, and it doesn't even go inside the circle. So the line at the bottom that touches the circle at two places is what we call the secant line. And the one that touches the circle at one point is called the tangent line. Now in calculus, we use secant lines and tangent lines also, and we especially use tangent lines. You'll notice on the graph I have a similar thing to what I had on the circle on the left-hand side, and so I have a secant line that touches the graph at two places, and I have a tangent line that touches the graph at one place. And that tangent line is really, really important. Actually, mathematicians spent many, many years trying to figure out how do we find the slope of that tangent line, because the slope of the tangent line tells us the rate of change of the function, and so it's really, really important. And they realized that they were able to find it using limits, and that the slope of the tangent line was what we call the derivative. So let's first talk a little bit about how to find the slope of the secant line. So you'll notice I have a graph. I only have variables on the graph. And so I'm going to show you where the derivative actually comes from. So if I have this line here, if I want to find the slope of that line, I need to figure out the x-coordinate and the y-coordinate. I called the second point just x, so that's going to be the point x and f of x. Then this one I called c, and so that's going to be c, and f of c are going to be my 2 points. So the slope of the secant line is going to be the same way that you've been finding the slope for probably like 4 years now, or maybe 3 years, depending on how long you've been finding slopes of lines. You do the change in y over the change in x. And the y value for the x part of it is going to be f of x. The y value when x is c is going to be f of c. The x value when x is just going to be x, and then the other x value is c. So this right here is the slope of the secant line. So you'll notice I also drew a line on the left at c. This time I drew the tangent line. And to find the slope of the tangent line, we're going to use a similar idea to the secant line, except there's a little bit more going on. So don't write down this next stuff that I'm going to do. It'll just make your notes look really confusing. So in order to find the slope of the tangent line, we need to use our idea of how we found the slope of the secant line. But you'll notice like the secant line that we have drawn right now, that looks nothing like the tangent line. They almost look perpendicular. However, if you make that x a little bit closer to c like that, you get a little bit of a better estimate. And then actually, if you go even closer to, if you make the x value a little bit smaller here, this x would be right there, you get an even better estimate. So if you keep on drawing like little lines that get closer and closer where the x value, the second value is closer and closer to c, you're going to get a pretty good estimate of the slope of the tangent line. So in order to actually find our estimate of the slope of the tangent line, we're going to take the slope of the secant line, but we are going to take the limit as x gets closer and closer and closer to c. So we are going to do the same thing that we just did, but we're going to have our x approaching c. So this is the slope of the tangent line. I'm also going to tell you this is what we call the derivative. And like I said earlier, in calculus we spend months on derivatives. We write this, by the way, as f prime of c. So that means the derivative evaluated at c. So we put a little tick mark next to our f. So let's do an example. And actually, before we do an example, I'm going to tell you right now, if you have no idea what I just talked about, if you really didn't understand it, that's okay. We'll do some examples. When you get to calculus, you will learn how to use that method that we just did, that formula that we just did, but you're also going to learn some shortcuts to use that are a little bit easier. So I'm just hoping that you get exposed to it and you try to understand it the best that you can right now. So for this example, we're going to do two things. We are going to find the derivative of f evaluated at 1. And we're also going to find the equation of the line that is tangent to the graph of f of x equals 2x squared at the point 1, 2. So let's start by drawing a picture. I always think that when you're first learning these, drawing a picture is really helpful. And we know that the graph of 2x squared, it's going to have a point at 0, 0, and then it's going to be a parabola, but it'll kind of be like a parabola with a vertical stretch that's going to be kind of compressed inward. So we do have a point at 1, 2. It goes up like that. So this is our point. So basically what we are doing is we are finding the equation of this tangent line that's right here. And so having a picture I think is helpful. You know it's going to be, you know the slope is positive. That means that the derivative is going to be positive. So that's something that'll help us out. It looks pretty steep, so that's also something that's going to help us. So let's go ahead and first find the limit using our definition of a derivative. So remember that f prime of 1 is going to be the same thing as the slope of the tangent line at x equals 1. So we have that formula from the previous slide. And then we find that by doing the limit as x approaches 1 of f of x minus f of 1 over x minus 1. And keep in mind that this one right here comes from that one there. So it's going to, and then same thing here also comes from there. It's going to be different depending on what value you are evaluating at. So when we do this, the first thing I'm going to do to evaluate this limit is plug in the function for f of x. So I get the limit as x approaches 1 of f of x, which is 2x squared. F of 1, we know that's going to be the y value when x equals 1. We know that when x equals 1, y is equal to 2. They actually even gave us the point for that one, so that was nice. This is all over x minus 1. So now, when you evaluate this limit, actually you can try this on your own if you want. I recommend you pause and see if you can evaluate the limit. So when you evaluate this limit, if you plug in 1 for the x, you will find that you get a 0 over 0. What that means is not that we have to stop and that we don't have an answer. It means that we have to find another method to find this limit. So the method that we're going to use is factoring. And so I'm going to start by factoring out a 2 from my numerator. And you'll notice that when I factor out a 2, I actually get a difference of squares in my numerator, which is nice because those are not too hard to factor. So I get x plus 1 times x minus 1 all over x minus 1. Now I can cancel those x minus 1's out. I get the limit as x approaches 1 of 2 times x plus 1. You'll notice I wrote my limit as x approaches 1 throughout the entire thing. Please make sure that you do that until the very end when you evaluate. Now I can stop writing my limit because I'm going to substitute that 1 in. So I end up getting 2 times 1 plus 1, which gives me f prime of 1 equals 4. So that gives me two things. That first gives me the slope of the tangent line, and it also gives me the derivative evaluated at 1. So now let's find the equation of the tangent line. And to find the equation of the tangent line, I'm actually going to do it over here. It's the same things that you've been doing for many years with finding graphs of lines. We have a point that's on the line 1, 2. We know our slope is 4. By the way, if you look at that slope, it does look pretty steep. It's positive, so 4 seems like a reasonable answer. So if you have a graph, it's a good idea to do that. I am going to find my equation of the line by using point slope form. Keep in mind, point slope form is y minus y1 equals m times x minus x1. If you take calculus, you are going to be using point slope form a lot because you're going to be doing this type of situation a lot. The x1 and y1 is just going to be the values of that point. So I get y minus 2 is equal to 4 times x minus 1. If you want to simplify this out to get it in slope-intercept form, you can. I like to simplify it out. When you do that, you should get 4x minus 2. And again, if you want to extend your tangent line and just make sure that it seems reasonable for 4x minus 2 to be your tangent line, you can do that. It is a reasonable tangent line. It does appear to fit onto the graph just fine.